So today we're going to be talking about cohort studies. Quick thing about the nature of epidemiology. Most epidemiologic studies are either observational or experimental, and observational studies are considered natural experiments, while experimental studies are considered true experiments. So we're going to talk about that in much more depth in a second. As we've discussed previously, epidemiologic studies can be classified as either observational or experimental. Each design represents a different way of harvesting information, so selection of one over another depends on the particular research question, concerns about your data quality and efficiency, and practical and ethical considerations in your research. The majority of epidemiologic work takes place in the realm of observational studies. However, much epidemiology and health services research is classified as experimental. Observational studies do not involve any investigator manipulation. There's no random assignment to groups, and researchers use naturally occurring groups for comparisons. Observational studies may be descriptive or analytic. We've previously discussed two types of analytic studies, the cross-sectional study and the case control study. Now today we're going to be covering the cohort study. We will also be discussing experimental studies later. Experimental studies involve the randomization of subjects into groups. True experimental designs involve investigator manipulation, as well as random assignment of subjects to the treatment groups. Experimental studies may be conducted on the individual level or at the community level. So you may randomly allocate the treatment at the individual level, or you may want to allocate the treatment at the group or the community level. Now there are two main time dimensions in research, cross-sectional and longitudinal. A cross-sectional study involves assessing subjects at one point in time, while longitudinal studies follow people over time. There are numerous types of longitudinal studies, including prospective studies that involve identifying subjects and then following them forward through time, retrospective studies, where you identify subjects and then look back in time, typically through the use of secondary data. We also have time series studies, and in time series studies, participants are sampled at different points in time, typically at baseline and then after treatment and potentially at another follow-up. Trend studies look at a variable over time but do not attempt to sample the same people. For example, a study might examine trends in car accident mortality over time in a particular geographic area. Now, a cohort study follows the same group of people over time. So observational designs, of course, are the foundation of epidemiologic research. The three broad types of epidemiologic designs that we cover in this course are the cohort study, the case control study, and the cross-sectional study. Now remember, all three of these types of studies are considered correlational designs. So which design do you choose? In theory, it's possible to use each design to test a hypothesis. As we walk through each study design, we'll talk about how the design could be used to study the relationship between a predictor variable and an outcome variable. Your choice of study design depends on a number of factors, including the state of the knowledge, frequency of exposure and disease, time, cost, and other feasibility considerations. And remember, each study design has unique and complementary advantages and disadvantages. So temporality refers to the timing of information about cause and effect, or the risk factor in the outcome. In order for a factor to be a cause of an outcome, it must precede the outcome in time. Though this seems self-evident, most observational research designs do not allow the researcher to actually assess the temporal relationship between the risk factor and the outcome. The majority of observational studies assess information on the risk factor and outcome at the same time, like they do in a cross-sectional study design, or they assess the risk factor after identifying the outcome, like we see in a case control design. So what is a cohort? A cohort is a population group or a subset of that group that is followed over a period of time. Now, a cohort may have a specific common exposure, such as an occupational cohort or a school cohort, or they may share non-specific exposure associated with a general classification, like a birth cohort, which is a group of individuals that were all born the same year. Cohort study designs begin with a group of people who are free of disease and who are classified into subgroups according to exposure to a particular risk factor of interest. Now, the whole group is then followed through time to see who develops the outcome of interest, and if the development of the outcome differs by exposure status. Cohort studies are the observational equivalent of experimental studies, but unlike experimental studies, the researcher cannot allocate the exposure. So the researcher must locate a natural experiment to observe the relationship between the exposure and disease. In cohort studies, we are examining incident cases, since you're beginning with a disease-free group of people. Cohort studies allow us to establish a temporal relationship between the risk factor and the outcome variables, meaning we're able to establish that the risk factor did in fact precede the outcome in time. Because of this, cohort studies are considered a much stronger study design than case control or cross-sectional studies for attempting to establish causal relationships between two variables. Now, we'll talk more about causal relationships later. Cohort studies can be prospective or retrospective. In a prospective study, you begin with your disease-free cohort, and then you follow them through time, identifying incident cases as you go. So if you begin your study today, you will follow up with people for the next 5 years to identify incident cases. In a retrospective cohort study, you have some type of data that allows you to assess exposure status in the past. So for example, 5 years ago. Then you are able to use existing data to follow through time and identify incident cases until the designated endpoint of the study. So for example, you might use military records to identify exposure to radioactive fallout at a nuclear bomb testing site. And then you can use those medical records to follow patients through time and identify those who developed incident cancer. So how do you choose between a retrospective versus a prospective design? Retrospective designs are generally cheaper and faster since the data already exists, and they are efficient for diseases with long latent stages, again since the data is already there. The use of existing data, however, may not have the information on exposures necessary for your study of interest. Prospective studies are more expensive and time-consuming, since the researcher must start at the beginning of the data collection process. This also makes them less efficient for diseases with long latent periods, since the researchers must wait for the outcome to develop. Prospective studies do provide the advantage of allowing the researcher to collect exactly the exposure and outcome information that they need. And these types of studies are also less vulnerable to bias than retrospective studies. So in cohort studies, we do not begin with diseased individuals. We begin with people who do not have the disease of interest, but that do have some exposure of interest. So how are we selecting our exposed population? The choice depends upon the hypothesis under study and the feasibility of obtaining that population. Some examples of exposed populations include occupational groups, groups undergoing a particular medical treatment, groups with unusual dietary or lifestyle factors, professional groups such as nurses or doctors, or students or alumni of colleges, or we can use geographically defined areas. For rare exposures, you generally need to assemble a special cohort, such as an occupational group, or groups with special diets. An example of an exposure-based cohort would be rubber workers in Akron, Ohio, where the exposure is an industrial solvent and the outcome is cancer. For more common exposures, you may want to use a general or population-based cohort that will facilitate accurate and complete ascertainment of data. This might mean a cohort of doctors or nurses, or a cohort from a well-defined community. An example of a general cohort or population-based cohort like this is the Framingham study that's described in your readings. So how do we ascertain exposure status in our cohort? If it's an acute event, such as a one-time chemical exposure at a plant, it's relatively clear who was exposed. However, exposure is not as easily determined in other circumstances. It is possible to ascertain exposure through existing records, such as medical records or birth certificates. This type of data is inexpensive, but the level of detail may be inadequate. Also, records may be missing and there usually is little information about potential confounding variables. We can also assess exposure through interview or self-administered questionnaires. Interviews and questionnaires are good for identifying information that's not routinely recorded, but they have the potential for recall bias. We can also directly measure exposure using physical exams, tests, or environmental monitoring. Finally, we can use proxy measures. For example, we can ask a parent to report on exposure status for their children. Now, you want the unexposed comparison group to be as similar as possible to the exposed group with respect to all factors except the exposure. If the exposure has no effect on disease occurrence, then the rate of disease in the exposed and the comparison groups will be the same. There are three possible sources of comparison groups. You can have an internal comparison where the unexposed members come from the same cohort as the exposed members. For example, in the Framingham study, both unexposed and exposed individuals came from the geographically defined area of Framingham, Massachusetts. You may also have a comparison cohort, which is a cohort who is not exposed and is from another similar population. For example, you may want to compare asbestos textile workers to cotton textile workers. Finally, you can use pre-existing data from the general population as the basis of comparison. The general population is commonly used in occupational studies. Now, the goal in a cohort study is complete follow-up on all subjects, regardless of exposure status. You can use blinding to ensure that there is comparable ascertainment of outcomes in both groups. Sources of outcome information are similar to those sources utilized for ascertaining the exposure status. In any cohort study, the ascertainment of outcome data involves tracing or following all subjects from exposure into the future. This is a time-consuming process, but high losses to follow-up raise doubts about the validity of your study. Some resources used by investigators to conduct follow-up include town lists, polk directories, telephone books, physician and hospital records, birth, death, and marriage licenses, driver's license lists, and relatives and friends. Now, the basic analysis of cohort studies involves calculation of the incidence of disease among exposed and unexposed groups. Depending on the available data, you can calculate cumulative incidence or incidence rates. Now, recall that a fixed cohort consists of exactly the same people for the entire length of the study. A fixed cohort allows you to calculate cumulative incidence, and therefore your measure of association is the relative risk. A dynamic cohort is one in where people may enter or exit the cohort over the course of the study. Because dynamic cohorts use person time, we are able to calculate incidence rates. Our measure of association for dynamic cohorts is the rate ratio, which is also sometimes referred to as the incident rate ratio. Now, the measure of association for cohort studies with a fixed cohort is known as the relative risk, or sometimes we hear it called the risk ratio. The relative risk represents the strength of an association, and it is the ratio of disease in the exposed group to disease in the unexposed group. Stated differently, it's the probability of disease given the exposure divided by the probability of disease given no exposure. In this example, we are looking at the risk of a long hospital stay, which is our outcome due to insurance status, which is our risk factor. The risk ratio is calculated by calculating the cumulative incidence among the exposed and dividing by the cumulative incidence of the unexposed. In this example, we end up with a risk ratio of 2.02. So what does a risk ratio of 2.02 mean? In a cohort study, we're beginning with a group of disease-free people and following them through time to see who develops the disease we are interested in. Therefore, we are actually calculating the risk of disease. So in this example, we can say that patients receiving Medicare or Medicaid are 2.02 times more likely to have a long hospital stay compared to those with other insurance. Alternatively, we might say that the risk of a long hospital stay is 2.02 times higher for people receiving Medicare or Medicaid compared to those with other insurance. Those two statements are saying the exact same thing, just in slightly different words. So the strength of the association is interpreted the same as the strength of the association for an odds ratio. So In this example, we found a moderate association between insurance status and length of stay. So the measure of association for a cohort study with a dynamic cohort is the rate ratio, also known as the incidence rate ratio. The rate ratio is also an estimate of risk of disease and is the ratio of the incidence rate in the exposed group to the incidence rate in the unexposed group. In this example, we are looking at the rate of breast cancer cases, our outcome of interest, by tuberculosis treatment, which is our exposure of interest. The study followed 1,047 women who were treated with air collapse therapy and exposed to numerous fluoroscopic examinations, and 717 women who received other treatments. A total of 47,036 woman years of follow-up were accumulated. We can calculate the incidence rate of breast cancer in the exposed group and the incidence rate of breast cancer in the unexposed group. If we take the ratio of the incidence rate of breast cancer in the exposed to the unexposed, we get a rate ratio of 1.9. So what does a rate ratio of 1.9 mean? In this example, we can say that the rate of breast cancer is 1.9 times higher in the exposed group compared to the unexposed group. You will often hear the rate ratio interpreted the same as the risk ratio. For example, women exposed to fluoroscopies have 1.9 times higher risk of breast cancer compared to unexposed women. Technically, we have not directly calculated risk. However, it is fine if you interpret the two measures similarly. Now, both the odds ratio and the risk ratio are measures of relative risk, meaning that they tell you the increased probability of getting the disease given that you have a particular risk factor compared to someone without the risk factor. They do not give you a measure of absolute risk or absolute excess risk. Attributable risk measures the excess risk, which is the added risk of disease due to the exposure. Population attributable risk is just the added risk of disease for the population. How much of this disease is due to the exposure of interest. Now, cohort studies are efficient for rare exposures and allow you to evaluate more than one outcome. If the design is prospective, you generally have good data on exposures and other key variables, and this design is less vulnerable to bias than other designs. Finally, cohort studies allow you to see a clear temporal relationship between exposure and disease. Now, cohort studies are inefficient for rare outcomes. If they are retrospective, you may have poor information on exposures and other key variables. If they are prospective, they can be expensive and time-consuming, as well as being inefficient for diseases with long induction or latent periods. A nested case control study is a case control study nested within a cohort study. So you've assembled a cohort, and at baseline the cohort is interviewed and samples are taken. Later, after they've been followed for some time, you can identify incident cases of your outcome of interest and then select controls from your remaining cohort. You can then analyze samples or surveys from those individuals selected for your nested case control study to determine exposure status. Now, nested case control studies have the benefit of still being able to establish the temporal relationship since the data was collected prospectively.